Picture this. You walk into a room, your patient's on oxygen, and the gauge reads plenty of pressure. On paper, everything looks fine, but the gas isn't reaching the patient. So here's a question I want sitting in the back of your mind for the next 9 minutes. Are pressure and flow the same thing? Welcome to week 1 of Respiratory Skills 1, how gas behaves. Every respiratory device you will ever touch manipulates pressure, volume, flow, or resistance. So why does a respiratory therapist need physics? It's not to become an engineer. It's because three things happen when you understand what's going on when it doesn't do what you expect. And you can explain it to a patient, a nurse, a physician, asking why the numbers look the way they do. Four big ideas. Everything else this semester hangs on these. So it's important you take the time to understand them. So pressure is force spread over an area. Think of it as a driver. It's what makes gas want to go somewhere. Volume is the space the gas occupies. At a constant temperature, pressure and volume move in opposite directions. And sometimes you'll say that as inverse, or they're inversely related. Flow is gas actually moving over time. Flow is caused by a difference in pressure between 2 points, not by pressure just existing, by pressure being different in 2 places. So resistance is the opposition to that flow, determined largely by how wide and how long the path is. So let's sit on this for a second. Pressure, volume, flow, resistance. When something goes wrong with a device or a patient, one of those four is almost always the answer. Your job is to figure out which one that is. So here's a challenge for you. Pressure is present, so where is the flow? Which brings us back to the scenario from the top. There's adequate pressure at the source, but not enough gas reaching the patient. Is there actually a pressure gradient driving gas from source to patient? Is the tubing kinked or narrowed somewhere along the circuit? Has the resistance gone up? Has the tube got smaller? Is the flow becoming turbulent? Is the device even assembled correctly? I'm not going to solve this one for you. We're going to solve it together in class after all 3 videos. For now, this is where we are headed, and I need you thinking. So what is actually pressure? So pressure is force divided by area. But here's what's physically happening with pressure. Gas molecules are constantly in motion, right? And they never sit still. Every time one slams into a surface, it exerts a tiny force. Pressure is all of those collisions added up and spread across the surface they're hitting, which gives you 3 ways to raise it. Pack more molecules in the same space will give you more collision, raising your pressure, or you could heat them up and they move faster and hit harder. So clinically, a ventilator generates a pressure difference to push gas into the lungs. That's the machine in one sentence. Now, respiratory care has a habit of measuring pressure in about 5 different units, depending on what we're looking at. So I wouldn't really focus on memorizing the conversion table, but you do need to recognize which units belong to which context. So we'll go over those. Centimeters of water they're abbreviated. That is used for ventilator and airway pressures. Millimeters of mercury is also called torr, is typically used for blood pressure and gas partial pressure. And you have kilopascals, that's commonly called international or common internationally. Pounds per square inch, abbreviated PSI, and we usually equate that to cylinder pressures like an oxygen tank. And atmosphere is exactly what it sounds like. Altitude and hyperbaric work will be measured in atmospheres. So quick rule of thumb, if it's a tank, we're going to think it's PSI. We're taking in terms of PSI. And if it's a ventilator, we're thinking in terms of centimeters of water. If it's blood, millimeters of mercury. Here's a slide that's going to matter a lot here. Gas does not move because pressure exists, like we said earlier. Gas moves because pressure is different in 2 places. That difference in pressure is the gradient. And we denote that by a delta symbol and P. So high pressure zone on one side, a tank, a ventilator, or the atmosphere, right? And then low pressure zone on the other side, the lungs. Gas runs downhill, so high to low. And that's usually how it happens every single time. And this is where the clinical challenge. A gauge tells you about pressure at one point. It tells you nothing about whether there's a gradient between 2 points, and also nothing about what might be in the way. Here's your conversion reference. Notice it, bookmark it. Most equipment displays pressure in the units that's normal for the application, so you'll probably convert less often than you'd expect. One line worth carrying in your head is 760 millimeters of mercury equals 1 atmosphere. And we'll practice some of these conversions live in class. Boyle's Law. Fixed amount of gas, constant temperature. Hold on to those two conditions. Under them, pressure and volume are inversely proportional. And there's a formula, P1 V1 equals P2 V2. So, an example, take a syringe, and if you cap the tip or put a cap over the tip, push it in the plunger, you didn't add any gas. You just gave it less room so the molecules collide more often and pressure goes up. So if you ever have done that before and you press a little too hard, sometimes you'll blow the tip off the end of that plunger, releasing the gas or the fluid, whatever's in it. The product of pressure and volume stays the same. And that's why the formula works. And this is Boyle's Law in the body. So when your diaphragm contracts, the thoracic volume increases. The alveolar pressure, that drops below atmospheric, and the air flows in. When the diaphragm relaxes and comes back up, the volume decreases and the alveolar pressure rises above atmospheric, and now the air flows out. And here's a distinction I want you to hold on to because it's going to come up again. Both spontaneous breathing and positive pressure ventilation use the pressure volume relationship, but the order is reversed in either one. So in spontaneous breathing, volume changes first. The chest expands and the expansion creates that pressure change. Positive pressure ventilation, the pressure changes first, right? The ventilator rises airway pressure and that pressure produces the volume change. So volume first versus pressure first. Two supporting laws before we wrap up, and both of them are about temperature. So there's Charles' law, where it's pressure held constant, volume and temperature move together. So pressure held constant, pressure doesn't change, the volume and temperature move together. Warm gas expands and cool gas contracts. Guy-Lussac's law is volume held constant, pressure and temperature move together. And this one has some teeth to it. Take a sealed oxygen cylinder. The volume can't change in that oxygen cylinder. And if you leave it in a hot car, right, the temperature climbs and the pressure inside that tank climbs right along with it. And that's the safety issue. So stop and think. Write this one in your notes. A pressure gauge shows adequate source pressure. Does that guarantee gas is flowing to the patient? Why or why not? Here's where I'll leave you. Pressure creates the opportunity for flow. It doesn't guarantee it. Whether gas actually moves depends on the gradient between 2 points. And there's one more layer. Gases aren't all alike. They differ in concentration, in density, and how thick they are. And that's what we'll be going over in video 2, gas mixtures and gas properties.